Okay, let's continue the discussion of graphs of a function and inverse function. The graphs of y equal to fx and the graph of y equal to f inverse of x are symmetric with respect to the line sorry, the line y equal to x. Okay, so this line y equal to x is the diagonal of the first and the third quadrant. The reason is that, remember that when we get the graph of a inverse function, we actually interchange the position of x and y. And also we know that the point AB and BA, if you exchange the x and y coordinate, these 2 points are symmetric with respect to the line y equal to x. This line has a slope positive 1. Whenever you have AB and BA, you connect them, this segment has slope -1. You can check that the slope is exactly -1. And it's the distance from the points to the diagonal are equal. Okay, so that's the reason why the graphs of those two functions are symmetric with respect to this line. Okay, so next, so usually it's not that easy to determine if a function is one-to-one or not, because once it is one-to-one, you can define the inverse function. But how do we know it is one-to-one, right? This place, we are going to list a remark. This remark depends on the differentiability and the mean value theorem. And we have to claim that the mean value theorem will be discussed later. And so far, we just use the mean value theorem. And this usage does not give us a loop of the logic, because mean value theorem does not depend on this result. This result can be considered as the application of mean value theorem. We can put this after the mean value theorem. It's okay. But here we just list it as a remark. Okay. So if f is differentiable, on an open interval, I, and f prime of x is not equal to 0 for all x in I, then f is one-to-one. On this open interval. Okay. So here I want to say a little remark about this remark. And this is a sufficient but not necessary condition. Okay, it's a sufficient but not necessary condition. Sufficient and necessary condition, we will say if and only if. And if it's just sufficient, so we only mention one direction. The example is the following. So if you have y equal to x cubed, then y prime is 3x squared. Y prime is 3x squared. Then we know that y prime of 0 is equal to 0. But we also know that y is 1-to-1. The function y is 1-to-1 on the set of all real numbers. Remember that the graph is like this for the for the cube function. So it is always a one-to-one, but at this point, it has a horizontal tangent. Okay, so this implies sometimes you have a one-to-one differentiable function, and it's possible to have a zero derivative. It's not that it's not impossible, but if it does not have a zero derivative, then definitely it's one-to-one. Okay, so this is a remark about the remark. Okay, now let's see the proof. The proof depends on the mean value theorem. What is the mean value theorem? If f is continuous over the closed interval AB and the differentiable over the open interval AB, then there is a number C in the open interval such that f prime of C is equal to fb minus fa over b minus a. Remember that we just compare the slopes of two segments. One is this second line, and the other one is the tangent line, right? This is point C, A and B, right? So we compare those two slopes, definitely you have it. So that's mean value theorem. Okay, so we are going to use mean value theorem in this proof. Assume that f is not one-to-one on this open interval I. Not one-to-one, then there exists a, b in this open interval with, first of all, a is less than b, or a is greater than b, either way, but a is less than b and fa is equal to fb. Okay, so it's not one-to-one. Then we collect the information. The function f, we consider it from closed interval AB to the set of R, is continuous over the closed interval AB and differentiable over the open interval AB. Over the open interval. So here we only use the condition that A is less than B, so we can construct the open interval and the closed interval this way. If you do assumption the opposite way, then you have to use BA. Okay? So this additional requirement is used here. And the continuity and differentiability comes from the assumption that f is a differentiable over this even larger open interval I. All right? So we can apply by the mean value theorem. By the mean value theorem, there is a number C in the open interval such that f prime of C is fb minus fa over b minus a, right? B minus a denominator makes sense because a is not equal to b, and fb minus fa, we know fb equal to fa, it's equal to 0. It is equal to 0. This contradicts the fact that f prime of x is not equal to 0 for all x in I. right? AB is containing I, so you do find a C such that f prime C equal to 0, but here you assume f prime of x is never 0. This implies, hence your assumption is wrong. Hence f is 1 to 1 on the open interval I. Because you have this assumption, you get this contradiction, right? Okay, so we do solve this problem, or we prove it. Now let's use this remark to do some example. The example says prove that fx is e to x minus e to negative x is 1 to 1 on R. And find a formula. Find the formula for F inverse. Okay, find the 1 inverse formula. To show it is 1 to 1, we are going to apply this remark. Let's try to compute the derivative. F prime e to x minus negative e to negative x, right? By the chain rule, it is equal to e to x plus e to negative x. And we know that exponential function is always greater than 0. The addition is also always greater than 0 for all x in R. Okay, then by the remark, fx is 1 to 1 on R. Fx is always 1 to 1 on R. So we finished the proof part. And now let's try to find a formula for the inverse function. How do we find the formula for the inverse function? We let y be e to x minus e to negative x. 1 over e to negative x is 1 over e to x. So we multiply this equation by e to x, we will get e to x times y is e to 2x minus 1. And this, you simplify it, is e to x minus e to 2x minus e to x times y, and minus 1 equal to 0. This is an equation quadratic in e to x. This is an equation quadratic in e to x. All right, so by the root formula, we get e to x is 2a negative b. Be careful here, b is negative y, so negative b is positive y, plus or minus square root of a b squared, negative y squared, it was, minus 4ac. C is negative 1, so that's why a is 1. So it's a y plus or minus square root of a y squared plus 4 over 2. Remember that we have a observation that this y here, we observe that y minus square root of a y squared plus 4 is always negative. Always negative, right? Because its absolute value is less than it. Okay, but we know that e to x is positive for all x in R. So e to x can only be y plus square root of a y squared plus 4 over 2. The negative sign, negative choice is removed. All right. Okay, negative is removed. Then we take the natural log. So the y equal to the natural log, the numerator, over the denominator. So this is f inverse of x. This answer, the formula of the inverse function. All right. Okay, So that's the example about the application of a remark. And next, we stop for the discussion of a one-to-one function for a moment, and let's study the countability. We are trying to count the number of the element in one set. The definition. Let E be a set. E be a set. E is said to be finite. E is a finite set if and only if E is either empty. Empty set, we consider it as a finite set, or there is a natural number n and a one-to-one function f from the set 1, 2, 3 up to n onto E. Okay, so it has to be one-to-one, and this map should be onto. So basically, it is a bijection. There is a bijection between 1 to n and E. This way, we consider it as a finite set. Okay, and second, E is said to be countable if and only if there is a one-to-one function. There is a one-to-one function from natural numbers onto E. Natural numbers onto E. So there is a bijection between n and E. Between n and E. Then this is called countable. In this book, countable and finite, they are separate because countable has infinitely many elements. Finite just have finitely many elements. Later we will see there is a big difference between them. Okay, but sometimes in other books they may consider finite as one type of a special type of a countable set. So you just read the book and make sure you they have same or different definition about the countability. Okay. 3. E is said to be at most countable. At most countable if and only if E is either finite or countable. So in the third definition, they combine the first two situations and call it at most countable. Why we put these two types of a set together? The thing is that finite, you can say first, second, third, nth term, nth element, and you stop. Countable means first, second, third, nth, n plus 1, n plus 2, n plus 3. You can still continue to count it, but without termination. So but either way, you can count 1, 2, 3, 4, can count. One stops, one does not stop. But to count them, It's a similarity. So that's why they call it at most countable. Of course, there are sets which cannot be counted. Then we say it uncountable. E is said to be uncountable if and only if E is neither finite nor countable. You see, countable, either you finish in several steps or you never finish. So there are only two possibilities, finite and countable. If you, after infinitely many times counting, you still miss some number, that's uncountable. So it is opposite side of a finite and a countable case. So uncountable and at most countable, they are totally separated. There's no overlap. Okay. So let's see. To show a set is countable, to be countable, not is countable, to be countable. To show a set to be countable, we need a one-to-one function from n onto e, from n onto e. Okay? So for example, we let E be the set of all even numbers. The set of all even number, even natural numbers. And we define f of n to be 2n from n to e. And then this f is 1-to-1 and onto. F is 1-to-1 and onto. So the set E is countable. The set E becomes countable. But we also know that the set E is a subset of natural numbers. A natural number, of course, is countable. Countable, basically, we understand them as the same. If you two sets are both countable, they are both listed as the first, the second, third, fourth element, then they have the same number of elements. So E as a proper subset is a proper subset of n, and E and n have the same number of elements. How do we know they have the same number of elements? We'll have one element here, you have one element here. You have a one-to-one correspondence, then we say they have the same number of elements. That's a special property. We know that if a set B is finite, then any proper subset A of B has strictly less number of elements. If you have a subset of with 3 elements, then any proper subset will have less than 3 elements, right? It can have 2, it can have 1, it can have nothing. If it's a proper, we emphasize it's a proper. Proper means it's not equal to the original set. But for the infinite set, you can find a subset so that the proper subset and the original set have the same number of elements. This is the serious difference between finite set and infinite set. Okay, so here we actually have the following, we can have the following definition. A set is an infinite set if and only if there is a proper subset so that let's use B, a set B, so that A and B have the same number of elements. A proper subset can have the same number of elements, then this is a infinite set. That's a definition. It can be the definition. All right. And from this definition, not from the definition of, we know that countable sets are infinite. Countable sets are always infinite because it has a one-to-one correspondence with the natural numbers. Okay, it's not a finite. Well, but not all infinite sets are countable. Not all infinite sets are countable, so there are sets which are not countable. In other words, uncountable. There are sets which are uncountable. So how do we find an example of an uncountable set? That's the next remark. This is a nice construction done by the counter, so it's called the counter's diagonalization argument. Okay, counter diagonalization argument. It shows that the open interval 0, 1 is uncountable. Is uncountable. The set of this open interval is uncountable. Okay, so this is a very, very good construction. You must memorize it. It's a very, very good construction. Okay, so let's try to prove it. Well, it's uncountable. How do we prove it? We assume it's countable. Countable, then there is, by the definition, there is a one-to-one function f from set of natural numbers onto 0, 1. Onto 0, 1. Okay, so we have f1, f2, f3, and 4 continue. This exhausts the elements of the 1 because it's onto. Onto means it will cover all possible elements from 0, 1. To do this proof, we are going to construct an element x in 0, 1 so that x is not equal to fn for all n in a set n. We're going to do this construction. How do we do this construction? Here we are talking about the structure of the real numbers. Real numbers have rational, irrational numbers. Rational number, either they are finite decimal numbers or it's infinite but periodical decimal numbers with repeated segments. Irrational numbers are just decimal numbers, infinite decimal numbers, but without stop, without repetition, without stop. Okay, so for each number fn, you can write it in the decimal expansion. We write fn in a decimal expansion. Okay, and when we do such expansion, there's a small thing. This expansion may not be unique. May not be unique. Why it's not unique? For example, 0.1, it is equal to 0.099999. Right? We can show that this is this equality is correct. If it's not unique, then it's a problem. So in this expansion, we require that the decimal expansion does not terminate the decimal expansion does not terminate in nines. We do not allow it. We do not allow this one. Actually, this can only happen if you have a finite decimal number. If you have infinite decimal number, this situation will never happen. It will only happen if you have finite decimal number. Finite decimal number, we only write it in a finite decimal number. There's no repeated 9 here. Okay, we require all the decimal expansions does not terminate in 9s. Then fn and 0.alpha-n1, alpha-n2 are one-to-one corresponding to each other. So we do have a unique decimal representation. Okay, so we have unique decimal representation. Now let's see the diagonalization argument. So we listed them. F1 as a 0.alpha-11, alpha-12, alpha-13, alpha-14, and so on. F2, 0.alpha-21, alpha-22, alpha-23, alpha-24, and now let's write 2 more lines. 0.alpha-31, alpha-32, alpha-33, alpha-34, alpha-4, 0.alpha-41, alpha-42, alpha-43, alpha-44. It's an infinite matrix, looks like. Okay, it's an infinite matrix. So here, all alpha ij are digits. 0, 1, 2, up 9. And none of them terminates in 9s. You do not have 9 forever. We don't allow that. And then we can have the correspondence. Okay, so that's how we list all the numbers in the interval 0, 1 if it is countable. Now let's try to construct the missing ghost. So let x be the number. X is 0 point beta 1, beta 2, beta 3, and so on. With what is a beta? Beta k is, I'm going to, okay, I will claim that x is not equal to f1. How do I do that? I just say beta 1 is not equal to alpha 1. And I'm going to claim x is not equal to f2. Well, I'm going to say beta 2 is not equal to alpha 2, 2. Then x is not equal to f3. Then beta 3 is not equal to alpha 3, 3. Okay? So how do I know that beta 1 is not equal to alpha 1? I just use alpha 1, 1 plus 1. Let it to be beta 1. That's enough. Right? Alpha 1, 1 plus 1 is equal to beta 1. Then everything is done. The thing is that alpha 1, 1 could be 9. If alpha 1, 1 is 9, then 9 plus 1 is 10. You have to move one unit forward. That's not what we want. So we want, if this alpha kk is less than or equal to 5, I use alpha kk plus 1. If it's not too big, we add 1. If it's too big, we do not do addition. We can do subtraction. The essential requirement is that beta k is not equal to alpha kk. That's an essential requirement. And also, I don't want this x terminates in 9, 9, 9, 9, 9. I want to avoid 9. So that's why here we subtract 1. Here we add 1. Okay? Okay, good. Then by this construction, then beta 1 is not equal to alpha 1, 1. Beta 2 is not equal to alpha 2, 2. And the beta n is not equal to alpha n, n. So x is not equal to fn for all n in the set of natural numbers. And we also know that x belongs to the interval 0, 1. It's inside 0, 1, but it's not equal to fn. This contradicts the fact that fn exhausts 0, 1. Remember, right? We claim it will exhaust the element of 0, 1. But here you do construct an element which is outside of the range. So that's a contradiction. The contradiction give us the result. Hence, 0, 1 is uncountable. Uncountable. So there's no way to count the natural numbers in a set 0, 1. Okay? Okay, very good. So this is an example, uncountable set example. The next, we are going to examine some common sets. For example, we want to study set of integers, set of rational numbers, and a set of real numbers. To study those countabilities, let's first discuss some basic property. So first, we study some property, some general property. After the general property, we will give you the statement about the ZQR. N is countable. NZQR, N is countable, so N is nothing to discuss. So we start from ZQR. Proof. not proof, sorry. Statement 1.36 lemma. First, a non-empty set E is at most countable. So we want to first classify the at most countable set. A set is at most countable if and only if there is a function g that takes n onto E. Takes n onto E. This condition looks very familiar because when we define countable set, not at most, when we define countable set, we say if there is a one-to-one function taking n onto Z. If you have countable, you need one-to-one. If you have at most countable, then you don't need one-to-one. That is the difference. Okay? So the difference between this lemma and the definition of a countable set is this one-to-one or not. With one-to-one, countable. Without one-to-one, at most countable. Okay? We'll see the proof. Let's see the proof. The proof is not difficult. It's a very neat proof. Okay, let's assume E is at most countable. So E is countable. Then by the definition, there's nothing to prove. Because in the definition, you do have such G, function G. Actually, it's even stronger. It is one-to-one function, but here, I don't care one-to-one or not. So for the countable set, it's natural if E is finite. Right? At most countable means either countable or finite. So if E is a finite, by the definition, there is an integer n such and a one-to-one function f that takes 1, 2, 3 up to n onto E. Okay? That's the definition. And the important thing is that it is onto E. We actually use this. And then we define G of J to be either f of J if J is less than or equal to n, or f of 1 if J is greater than n. So for the first n indices, we use f. After n's indices, we just use the first value. You can use whatever value, it doesn't matter. Any value inside E will be okay. Or just repeatedly use it. Either works. Then this G takes n onto E. So the important thing is that this is onto. So we also define this function. So from the at most countable, we can easily get the result. All right. Then next, we're going to prove the converse. Conversely, suppose that G takes n onto E. Takes n onto E. So we need to construct You need to construct a one-to-one function. F from either n or a subset of n onto E. So this time we have to emphasize it's one-to-one and it is onto. Two situations. The one-to-one is more important. Onto is also important, but onto is already guaranteed by G actually. Okay, so how do we do that? First, step 1. Let K1 be 1, the initial point. And E1 is a set of natural numbers, so that the G of a K is not equal to G of a K1. G of a K is not equal to G of a K1. So you have two situations. If E1 is empty, E1 is empty means for all GK, for all K, GK is equal to GK1. If E1 is empty, then E is equal to GK1. Is finite. Finite is at most countable. Okay, so this is done. If E1 is not empty, E1 is not empty, let's continue. It's a subset of natural numbers by the well-ordering axiom. There is a least element. Let's call it K2. Be careful. In E1, you have K2. In E1, you have K2. Okay? That's a least element. And define E2. It's a second. Yeah, it's really exactly a second. E2 is K in N such that GK is not equal to GK1 and the GK is not equal to GK2. GK is not equal to GK2. Okay? The K2 is in E1. Least element is in E1. Alright? And this part, what we get? We get K2 is strictly greater than K1. And K2 is greater than or equal to number 2. K1 is equal to 1. So K2 is greater than 1, so it's greater than or equal to number 2. Alright, so that's a condition. And once you have a set, you need to discuss. If it is empty set, then E is equal to G of a K1, G of a K2. And these two elements are different. It's finite. At the most countable. Alright, so it's done. If the set E2 is not empty, it's a subset of natural numbers, and by the well-ordering axiom, there is a least element, K3. In K2, you have K3. You always get the next index, the K3, and E3 is the set of a subset of natural numbers. GK is not equal to GK1, GK is not equal to GK2, and the GK is not equal to GK3. Okay, and also we have K3 is greater than K2, greater than K1, and the K3 is greater than or equal to 3. Okay, so have you seen the pattern? We're going to repeat. So continue this process. Continue this process. If it ever terminates, like whenever you have an empty set at a certain step, then E is going to be equal to G of a K1 up to G of a Kn is finite, at most countable. If it never terminates, then we have a sequence. We have a sequence K1 less than K2 less than K3 and less than infinity. And Kj plus 1 is the least element of Ej, and Kj is greater than or equal to J. Okay, Kj is greater than or equal to J. Okay, so let's do the construction. So we define Fj to be G of Kj in this case when it never terminates for all j belong to the natural numbers. And then we show that F is 1 to 1. F is 1 to 1. Okay. For j less than L, j is not equal to L. J is not equal to L. You have a small number, you have a large number. So for j less than L, then we have Kj less than KL. Kj less than KL. So Kj less than or equal to KL minus 1. Okay, they have the one by one. So Kj is less than Kj is less than KL, but it's less than or equal to KL minus 1. Okay, then by construction, GKL, it belongs to EJ. See, KL is the least element, so it belongs to the EL minus 1. EL minus 1 is K belongs to N. GK is not equal to GK1. GK is not equal to GKL minus 1. Okay, GK is not equal to L minus 1. This last index coincides with this index. So Kj is less than or equal to it. So GKL is not equal to GKJ because Kj is one of them. So we do have the 1 to 1. So F is 1 to 1. F has to be 1 to 1. Onto it's because for any x belong to where is it? X belong to E. Yeah, E. X belongs to E. There is an N such that X is equal to G of N. And because it's E1, E2, E3, they exhaust the whole set E. So there is an L such that X is equal to Gn is equal to G of a KL. G of a KL. So this part, you consider this condition. You get E1, E2, E3, E4. Eventually, you will exhaust the whole set E. So it will belong to one of a GKL. Then X is equal to FL. X is equal to FL. So F is onto. And then the set E is countable. And we are done about the proof. Okay, so if it terminates at a certain step, it's a finite set. If it does not terminate, it will be a countable set. Collect both cases, it's at most countable. All right, so we proved the theorem, and the next we're going to apply this and get more properties. Based on the properties, we can discuss the countability of the Z, Q, and R. Okay, so we stop this video and we will continue in the next video. Thank you.